we have discussed kind of the inspiral, and we obtained some
Maybe actually, yeah.
basic general idea quantitatively kind of what goes into computing these inspiral vectors. But now, so far we have considered the particles to be point particles. But now we want to take into account that these are actually compact objects that are strongly gravitating. And so just to say, what kinds of compact objects do we have to consider? Well, we know black holes with the no-hair theorem. All of the multipole moments are just the mass and spin, and all of the higher ones are built up about from those. We also have potentially black hole mimickers, because there are many theoretical puzzles about black holes still. For example, the information paradox, or how to interpret the huge black hole entropy microscopically when they are supposed to have no hair and be completely characterized by just two quantities. And there's a whole zoo of black hole mimickers that have been proposed for a review. I refer you to this article. You can read all about these. And typically what features of these black hole mimickers are that they are almost as compact as black holes. But when you look very near the horizon, there's not a horizon, but something else. It could be some fuzzy quantum structures, or just not a horizon.
Do we care in the spiral phase?
Well, this we will discuss.
Okay.
Yes, we will also discuss for the ring down, if time permits. Otherwise, some other occasion.
Yes.
People discussing the mimickers, do they come from an astrophysical background, or you mean theoretical background?
I mean, more, well, so this is, so the motivation for these mimickers is more from a theoretical background. But then you, of course, want to know what are astrophysical consequences of them. And then this review article was written, well, I think it was Vitor Cardoso and his collaborators, so more from a phenomenological side, I would say. Yeah, but really there's a whole zoo of them. Some of them I hadn't even heard of before. Then, of course, we also want to look at neutron stars, which add an interesting dimension to the problem, because they involve now really strongly interacting subatomic matter, or QCD, combined with strong gravity. So that leads to many interesting properties. Well, most of the matter is neutrons, as the name indicates, but they're already in some very weird state of a uniform liquid. And we still don't know how do all of these neutrons that in this liquid interact, and how do these interactions depend on density, and how are they different from nuclear interactions in terrestrial atomic nuclei, because those are isospin symmetric, so have kind of an equal number of protons and neutrons, whereas here it's very asymmetric, mainly neutrons, and so on. But then you can also do a magnitude calculation where you ask, well, beyond a certain density, the neutrons, what's the maximum density at which individual neutrons can be packed close together? And it turns out once you go above about 2 times the nuclear density, the neutrons start to overlap. So there's not enough space for individual neutrons. And then it's very likely that there could be a transition to some sort of deconfined quark matter, because then the quarks really become the relevant degrees of freedom. It will be a different phase of quark matter than in the quark-gluon plasma, because it's really at low temperature, dominated by all of these multi-body interactions, rather than in the quark-gluon plasma by the high temperatures. And there are also intermediate exotic phases that could appear. So all of this really is interesting to probe, and also for gravitational waves. Finally, we can consider objects that are made of new fields in the universe, where new fields are ubiquitous from many theoretical motivations. You can see some listed here. And it turns out if any kinds of new fields are present in the early universe, and you just, they start as random field configurations and you evolve that over cosmic time due to gravity and kinetic effects. They will start to form some sort of condensates of compact object-like configurations. And you can also have all of these extra fields either in or around all of the other objects we discussed. So clearly we want to now ask, can gravitational waves tell us about all of these properties? And in these lectures, depending on the time, we want to consider two aspects, since we are specializing kind of to non-spinning objects. So for the in-spiral, what we can learn from tidal effects, which are driven excitations of the quasi-normal modes of the object, which means basically because if one object is in the binary, the companion is orbiting from its point of view and is exerting a time-varying tidal force that changes on the orbital time scale. But then the orbit sweeps up in frequency during the in-spiral, so the tidal force also goes through a wide range of frequencies and can excite a mode of the object, either resonantly or adiabatically. And all of this can give an imprint in the gravitational waves. Then what happens after the merger is also, again, dominated by the modes of the object, but there it's not a driven excitation of individual modes, but kind of at the merger, if you think of that as kind of a perturbation of the final remnant in some sense, or at least after the merger, then it's the free oscillations of this final black hole that one sees in the gravitational waves. Okay, so let's start with the in-spiral and tidal effect.
Sorry.
Yes.
So you mentioned before, like some environmental effects, for example, clouds around.
Yes.
Do you have any reference for these things, like computations being in the framework of like Post-Newtonian or Post-Minkowski and taking into account such effects? Do we have a power counting for this?
Yes, so far all of the studies have been done in kind of Newtonian approximations, so not from the fully rigorous side, but more scoping out the phenomenology that could occur and seeing is it worth now the rigorous calculation. So I don't have, I mean, I can give you references to the kinds of more Newtonian calculations if you want.
If you have in mind.
Yes, later. Yes, let's do it later. More questions?
In the Newtonian sense, is they are included in a effective description, or?
Yes, so I mean, so they compute basically the state of, let's say, a cloud of fields around the black hole. I mean, for that is one uses relativistic black holes and the configuration of the cloud, but then the Newtonian binary companion perturbs the cloud, and there's depending on what kind of cloud you consider, then people have considered various levels of what's the feedback to the cloud. You know, if it's some cold dark matter spike, it could get heated up and then some of the dark matter will actually leave and things like that, or of these ultralight boson clouds that form these atomic-like structures. People also have considered all kind of level transitions that are induced and what's the effect on the orbit. But yeah, so they've really revealed very interesting phenomena and also what could happen with the orbit in these approximate ways. And yeah, if you're interested, then afterwards we can look up some references. Okay. So first, let's start with tidal effects, because that will already lead us to relativistic perturbations of compact objects, which we then also apply to the ring down signals. So if we just consider the simplest kind of tidal effect, which is adiabatic tides, so in a binary system, as we said, but now in a relativistic description, there's a Weyl tensor sourced by the companion. So there's some gradient in curvature, and the object responds to this by developing a different multipole structure than it has in isolation or would have in isolation. And for gravitational waves, we always care about what happens in the space-time. And here, the exterior space-time of the binary, how does the multipole structure differ from a spherically symmetric configuration, which in GR is not equal to the surface deformation of the object. That's an important point, especially for black holes. So we know black holes deform the horizon geometry in response to tidal effects, but actually this deformation measured in the space-time, at least for non-spinning black holes, is actually zero, as defined in this adiabatic sense. And so this deformation in the space-time will be proportional to the tidal field, which is a component of the curvature tensor. And this proportionality factor is sometimes called Love number or tidal deformability, sometimes with some normalization factors of compactness or radius or mass thrown in, but all of these are kind of equivalent. It's basically, we really need this response coefficient, which tells us about all of the internal structure information, or at least some, in the first approximation. Also, there's a reference if you want to get the full reference for how to match now this calculation of a perturbed object to an orbital space-time. This has been done once, and since then, the more widely used approach is to use the wordline skeleton approach, where these extended objects are modeled as center of mass world lines with additional structures that are the multipole moments. And it's also not so trivial in GR that you can actually do this, because that's really what you do in Newtonian gravity. But if you go to the papers from Dixon to 1970, which are really mathematical papers, they show that even in GR, it's still possible to do this kind of decomposition, but you have to be a bit careful how you define the multipole moments. Nevertheless, it turns out that in this picture then, the effective action for the binary system can be written as a point mass part plus finite size corrections. And for these tidal effects, again, the finite size effect, let's say in the Newtonian approximation, is basically a coupling between the induced multipole and the external field, and then perhaps some internal dynamics of the multipole. But in the adiabatic limit that we want to consider, there is no internal dynamics of the multipole moments. They are just static, and the tidal Lagrangian then reduces to something that depends only on these external fields, which depend only on the orbital quantities and the masses, and this characteristic Love number coefficient, which encodes all of the information about the object. And
So, and what happened? So when you do the match
yes,
function, what happened? So presumably the far zone,
yes,
it's unchanged.
yes.
You
In the
include-
far zone, it's unchanged, except now the multipole moments of the source are the multipole moments of the orbital dynamics plus the multipole moments of the objects themselves. So the total multipole of the binary system viewed from afar is now slightly changed, but all we saw for the far zone and so on post-Minkowski is unchanged.
And when we were considering the simplest case before, so at what point did we do the matched asymptotic expansion? So
We didn't actually do
we
it.
didn't do that.
I just said it turns out to be, yes, for the match asymptotic expansion, I really refer you to this paper of Blanchet and wait, let's go back, this review article. Okay, I have to go a while back that I showed there where you can see more details. Yeah, so this is a very long review article where you can find all the details. Sometimes it can also be nice to go back to some older papers where people go only to lower orders and maybe they were first discovering things. So it was still amazing to them that things turned out in this way. So for example, this one is quite nice to read, at least the introduction. So yeah, there you can find the details of the matching. But that matching was only between, yeah, kind of the exterior zone or the source physics for point masses and the wave zone. But here now we are adding in the fact that these bodies are not point masses.
And when you say we have to be careful with the definition of the multiples, is because the same happens that they're integrals that
Yes.
are not finite.
Well, in this case, basically because so in the previous case we had kind of a weakly gravitating source that we used the post-Newtonian expansion and then matched to the post-Minkowski. Here, the compact object is a strongly gravitating source. So actually the multipole moments you cannot write down as integrals over something. You have to extract them kind of by computing the perturbed spacetime of the object and seeing what's the multipole structure at large distances, and then matching to the orbital spacetime corrected by finite size effects. So yeah, here the multipole moments are defined differently than in the previous case. Yes, because we're really not making any weak field assumption for the object itself. Okay. Yeah, and then to let me just see what yeah, just to set up the
Can I ask
problem.
you about the tidal excitation?
Yes.
What's the difference between an adiabatic and resonant excitation?
Yes, the adiabatic excitation means the object just deforms kind of without oscillating, having any internal oscillations, or yeah, it just deforms a bit, but it's not near any mode resonance. Does that make sense a bit? So an adiabatic deformation is, you think in Newtonian terms, it just develops these tidal bulges, but they're not oscillating.
And then in the effective description that you were showing, that's just the adiabatic one.
Yes. Yes,
Well,
because
for the resonant one, you need a new word line.
no, for the resonant one, you need a different internal Lagrangian. You need for the yeah. So for the resonant one, you can still have this word line with the multipole moments, but then the dynamics of the multipole moments will be dynamical and not adiabatic. So you have here the coupling with the external field, but then you can have an internal Lagrangian that's just dependent on the dynamics of these multipole moments. And if it's resonant, then you would also have a kinetic and an elastic potential term for these multipole moments. And yeah, that's actually important, for example, for neutron stars.
No, but I mean, after, can you go one slide after this? In this case, you kind of integrated out the.
Yes.
So if you want to include the resonances, you add another Lagrangian.
Yes. So to include resonances, you have to go to this Lagrangian, which is more general.
It's probably the omega expansion, and that you can have as a local. If you just look around the static limit, you can do an expansion of the local variance of omega.
Yes, you
Yeah,
can
you can
capture
add that,
some
like-
frequency dependence, that's true. But to get the
But
full
those terms
resonance,
can be added in a form that's similar to this. It's just that it has additional time derivatives on the.
yes. So it's true, you could also have some effect, yes, also, yeah. either the time derivatives of the e's, or you could have an effective frequency dependent response or so. But if you really want to then also describe the in spiral, how it evolves through a mode resonance or so, I think the best bet is to include this Lagrangian, and then you just have all the equations of motion for the orbit coupled with this, and also the radiation reaction forces. Also, yeah, it probably is more complete. But yes, these other methods can also capture some of the effects. Any more discussion on? Okay, perfect. Yes, I should also say, of course, these kinds of, yeah, you also get if you consider just higher derivative operators and so on from an effective field theory approach, you would also write this kind of structures down. So now to compute this deformability coefficient that appears in this Lagrangian, we have to now consider perturbed compact objects. And again, we're in the non-spinning case, so the background is spherically symmetric. And we have to solve for the Einstein field equations and the matter equations of motion. And now we don't use the Landau-Lifshitz formalism. We could use it, but it would be a horrendous mess. It's much easier to work it, to go back to the original field equations and work in, yeah, with the full field equations, because the Landau-Lifshitz, as we said, is most useful when we can perturbatively expand for small perturbations to this Gothic metric. But here, because we're in the strong field regime, we cannot have such a perturbation. So we go back to the full field equations. Okay, and so we perturb the metric and the energy momentum tensor. And then let's set up some general formalism that we also come back to for the ring down. So let's say of non-spinning compact object. So we have the spherical symmetry of the background. So we can decompose the perturbations into spherical harmonics, because the perturbations they on the are just fields on the background space-time. And here we want to work with the YLMs instead of the STF tensor, but we saw already in the orbital Lagrangian we had the STF tensor. So at some point we also need to relate expressions in terms of these spherical harmonic expansions to the STF again. And it's also convenient to use a Fourier expansion. So some function of R and T we write now as the omega over, depending on your conventions, where you put the 2 pi, and again, depending on your convention, how you put the minus sign in the I omega T, tilde of R and omega. And one interesting result was in 1957, Reggie and Wheeler showed that when you do this decomposition and substitute, I mean, you apply this to both the perturbed energy momentum tensor and the perturbed metric, and you substitute this into the Einstein field equations, you find that actually these perturbations split into 2 different sectors according to their parity. Those sectors are then decoupled, which simplifies the problem. And what's meant by parity here is the reflection through the origin. So parity means plus or minus under theta and phi going to pi minus theta and pi plus phi. Okay, and this means actually that once we have six, I mean, in principle, we would have 6 degrees of freedom for these perturbations. But because of the two splitting between the two sectors, we actually have 4 in the even sector and 2 in the odd sector. So 4 in the even, 2 in the odd sector. And for the tidal effects, we now want to consider the even sector. At least for these kinds of tidal effects I talked about. There are also other tidal effects that require the odd sector. Yeah. So then we can write down the decomposition of the even metric perturbation. So integral d omega sum over L and M. Then we have these decomposed properties YLM, theta and phi. And then we still have 4 functions. And one can show that in the convenient gauge. We have one is the TT component. One is the TR component. Yeah, this here is called H1 conventionally. LM. Then it has to be symmetric, so H1 also appears here. Then there's an RR component one. It's usually called H2. And then there's one in the angular directions. So here 0, 0, 0, 0, 0, 0. And then here comes the angular, which is called KLM. And then the one for the phi is just with the sine squared theta. Think of all the zeros. But this is kind of the common notation following this original paper by Reddy and Wheeler. And we now have to solve the field equations for these functions H0, H1, H2, and K. So for the love numbers, we consider, because we are working in this static limit, we consider the limit of 0 frequency. And we come back to this full frequency dependence for the ring down equations. Okay, so then basically, yeah, I don't want to go through all of the derivation here, but what you have to do is you also have to decompose the energy momentum tensor into likewise spherical harmonics and Fourier modes, and substitute everything into the Einstein field equations. And then also recall that once you have L squared acting on YLM, it just gives you minus L times L plus 1 over R squared YLM. So in the end, you can cancel out all the YLMs. It turns out something, yeah, we don't have time to go in detail here. And in the end, you can find a master equation just for one of these metric functions, actually. And that you have to solve in the interior and the exterior. And from the exterior, you then have what's the space-time, you extract the quadrupole moment. Then you also extract what is the perturbing exterior field, take the ratio, and you have the love number. So what you get finally is you find something that so find that lambda is some function, let's say some function that depends on, let's say, the compactness, and then let's say the master function, we have solved the master equation in terms of H0. evaluated at r equals r, where r is the surface of the object. If it has a surface, depending on, otherwise you have to impose horizon boundary conditions. And typically this f is some combination of hypergeometric functions. So those you will see popping up because basically the exterior perturbations of Schwarzschild can be solved in terms of hypergeometric functions, and so that's why you always get these here. And the idea is then you have this kind of functional expression, and this you have to find from integrating the master equation in the interior. So that's in a blitz review of tidal deformability. All of now. Are there questions, or do you want more details, or anything we should discuss?
So when we plug in the Einstein equations,
Yeah.
do we get a separate equation for H naught, H1, and K, or are they all mixed up?
Well, they're all mixed up but you have different components of the Einstein tensor. So you combine different components and you can actually algebraically eliminate variables by combining. Yeah, also Reggie and Wheeler go through this a bit in their paper, how this can be done. And in the end, yeah, you find out you have an equation for H0 that depends only on H0 that you can solve. And then from that, you can reconstruct the other variables. And yeah, the reason for choosing H0 is just, it's in the time component of the metric, and then it kind of relates to, in a Newtonian sense, the gravitational potential, and then you can easily read off the quadrupole moment. That was kind of the reasoning. Okay, if there are no questions, then maybe let me write down here just for completeness from interior, so that it's now clear how information gets encoded in this lambda about the internal structure of the object. So this is really a key parameter for gravitational waves. And then let me just see if I have a slide. So here are some examples. If we take for neutron stars different models for the matter in the interior, we get different tidal deformabilities for versus mass curves. So taking a neutron star configuration, one neutron star is one point on this curve. And so each point is a different neutron star with a different central density, and different colored curves correspond to different equations of state. So that just shows, how information gets encoded in these parameters. You can also do it for other objects, say boson stars. You get a different result. You can even look at, if you have a modification at a Planck length from the horizon. So here in some just toy models, making some modifications, really the Planck scale from the horizon, and seeing, can Lisa measure this? Here's a tidal deformability then, and here these dashed lines, I believe, are how, is it measurable? And they concluded, it's not so crazy to think about probing Planck length corrections at the horizon with future experiments. Yes, okay, yeah. So
In those cases, you have to care about the odds components, or
no, it depends on, because okay. So here on the orbital scale, we kind of looked at this QIJ, EIJ coupling, but there are also, you can define, instead of the Q, some current type multipole moment that couples to some magnetic like tidal field. Because the EIJ is just one component of this Weyl tensor of the companion. There's also an odd component, which is yeah, somehow related to the dual of the Weyl tensor, which gives some field that looks like a magnetic field. Even it's sometimes called gravitomagnetic tidal field. So you would have this Bij tidal field coming from the odd component of the Weyl tensor or the dual, and yeah, that induces current multipole moments. Which you could call Jij. And of course, you can also do it, of course, for all the higher L tensors. And yeah, then you would get, then it's a bit more tricky. These odd parity modes are a bit more tricky to write down the Lagrangian, but you can still do it. Yeah, and then you have a different love number that is called the gravitomagnetic love. You actually have two love numbers in that case, which is also quite interesting. And then you match. So, yeah. Yes.
Maybe this is a stupid question, but is there a way to see how you connect the parameters that you have in the equation of state of the neutron star with the?
No, unless you go to really maybe Newtonian physics or so, because really, you have to solve numerically in the interior to get. So here, this H0 is determined. You find some equation for it that is just some coefficient. It depends where you put the coefficients. Okay, let me just write it in a simpler way. H double prime plus A, that now depends on G0 and T0. H0 prime plus some coefficient B that depends on G0 and T0. H that is equal to 0. And this you have to solve in the interior. So the equation of state comes in this T, but this is, these are, well, they're not so complicated functions, but you see if you have to solve this differential equation numerically, kind of this information is not so easy to get unless you really make a fitting function or something, how it depends on the equation of state parameters. And then that depends on the parameterization you have for the equation of state. If you, how you parameterize it. And plus then you have to plug it into this combination of hypergeometric functions to get the tidal deformability. So it's quite a nonlinear relationship. I mean, in principle, you can trace it, but it's, complicated.
And is the number of degrees of freedom in both sides of the matching the same, like in the equation of state of Newton? Same as in
no, because I mean, what you match is the love number. But in the equation of state, you have information on the composition. Well, okay, in the equation of state itself, you have only information on pressure and density. So the matching is really done at the level of the love numbers, which are kind of global properties of the object. And then this calculation tells you how to relate these global properties to the microphysics. I don't know if this answers your question.
Maybe a follow-up on the question. So one of the motivations I heard about getting these love numbers is that they might provide constraints on the equation of state of the music stuff.
Yeah.
And has any of the models actually been ruled out by the observations?
Excellent question. The neutron star merger event, DW 170817. Results for the neutron star tidal deformability. So this is the best data we have today for neutron stars. There were some other, at least one other binary neutron star event, but it was much farther away, so didn't give such good constraints. We have consistent results, but this is sort of the best measurement we have so far. What you see here is in a binary system, the love numbers enter through a combination lambda tilde, which is kind of similar to the chop mass. They also enter in an orthogonal combination, which is similar to higher order corrections, but this combination is kind of best measured. And what you see here is the result on this tidal deformability parameter. So only the horizontal axis kind of plays a role here. Anything between these orange vertical bars is consistent with the measurements. And these gray peaks are some equation of state models. And those are disfavored by the data. Does it answer the question? One caveat is, of course, this is the result assuming the neutron stars were slowly spinning. If you relax this assumption, then you get much worse constraints, which are not shown here.
Okay, if I understand. So then the delta tilde, then it's some combination of parameters that appear in the equation of state. Is that correct? Or
No, it's some combination of the masses and these tidal deformabilities of, so we have M1 and M2. Something like, oops, too many erasers here. So we have here M1, lambda 1, and M2, lambda 2 orbiting. And then this lambda tilde is some combination of their tidal deformabilities. It's similar to the chop mass. It's just a parameter that once you go through the calculation, it appears. I mean, then you find the dependence at the leading order is in this lambda tilde. And if you include more corrections, then you find different combinations. And then you can measure the individual ones.
yes, but how does it? I mean, because the question is, so the orange bar.
Mhm.
So it's more as an interval of.
Yes.
So how do you get the? So the question is, how does it disappear in the equation of state?
Yes.
So that's
So from the gravitational waves, you don't get directly a constraint on the equation of state. You constrain this lambda parameter, and then in the second step, you have to say how does it relate to equations of state.
okay.
Yeah. In principle, I think some people are working on kind of figuring out how to have directly equation of state parameters in the waveform instead of this lambda, but so far the only waveforms are with the lambda as far as I know. Because also one might want to be more broad and see, because this could be boson stars or some neutron star mimickers, or so maybe one wants to be a bit more open and leave it more general and then leave this interpretation to a second step. What does it mean to have this interval of lambda tilde? And then you can come with your favorite neutron star model and see, is it consistent?
Getting ahead of myself, since you mentioned spin.
Yes.
One of the things that I heard was that in spin this quadruple moment
Yes,
also depends on the equation of state.
that's true.
And is that more constrained, or is the tidal deformability gives you a better constraint?
It depends what object you're talking about. Because the spin-induced quadrupole moment, it's roughly scales like it scales quadratic in the spin. So, well, actually, let me also maybe give you the effect in the gravitational wave. Maybe, let me first, okay, now that we're talking about the spin. So Q spin would scale something like would be some other love number, kappa, which is the rotational love number times chi squared, where chi is the dimensionless spin. Yeah, it's S over m squared or something like this. And it's less than or equal to 1 for a black hole. So for neutron stars, they cannot spin at spin of 1. I mean, depending on the equation of state, they can spin maybe, I don't want to nail it down, but maybe 0.6 or so. It really depends on the equation of state. So chi squared for neutron stars is not so big, but for black holes, it could be larger. Because for neutron stars, we assume, as was also assumed here, spin less than 0.05. So if you assume that, the effect is relatively small. But one caveat is in the phase, which is where all the information comes in. So it roughly scales like kappa chi squared, and then v over c to the 4. Okay, but the tidal effects in the phase okay, maybe I can also say one more thing related to this for kind of the method that is used. So just to say, you now need a double expansion, as we already saw a bit. So we expand now in GM over RC squared, less than 1. And also, so this is the PN expansion. And then also we expand in R over R less than 1, where R is the size of the object. And small r is the orbital separation. So this is just in terms of when you set up your perturbative description, you now need 2 small parameters that are different. Because here you see this doesn't have any factors of C, so this is actually a Newtonian effect. And then, but here this has C. So that's a PN effect. So of course, for space-time dimensions and for integer multipoles, sometimes there can be degeneracies if you look at scalings with the orbital separation, but rigorously, mathematically, you should keep these actually separate. And then you find, okay, you also have now the total quadrupole of the system, like we said. So Qij of the system is now the orbital one plus the Qij of the object. So that gets modified. And then find, working perturbatively, delta phi tidal scales roughly like lambda v over c to the 5th. So now you can compare.
Is there a square missing? Because I thought the title was by PN effect.
Yes, b squared over c squared. Yes, perfect. Yes. So you see here, depending on what system you consider, for example, for black holes with spins much greater than 0.05, this effect will by far dominate. For neutron stars with very low spins, this probably tends to be larger. Also depends how early on in the in-spiral your detectors start to be sensitive, because this accumulates much longer. It becomes important much earlier in the in-spiral. So if that accumulates over a long time, then it can lead to larger corrections. And here, yeah, the tidal effects are mainly important at the end of the in-spiral. At least these types of tidal effects. There are also these other ones we didn't discuss that are also important earlier.
Where does the low spin hypothesis come? Like why are you?
Comes from observations of binary pulsars in our own galaxy, where most of these pulsars in the galaxy, they are relatively old, and especially when they then shrink the orbit due to gravitational wave emission, that takes millions of years. And the pulsars actually, they spin down due to magnetic field breaking, because their rotation, due to magnetic field breaking. So if they're very old and have been in the binary system for a long time, one can estimate how much will the spin be at merger. And for the galactic pulsars, people found it's much less than 0.05. But it's of course possible that not all binary systems are similar to galactic binary pulsars. And then the spin could be higher. And then we should not make this restrictive assumption. But it's likely that at least a large population of them might have small spin. But okay, this is still to be tested also.
I mean, in principle, there is this second population of recycled pulsars as they are known, right?
Mhm.
But in that case, the spin is still like 0.3 or something like that. At most, like the millisecond pulsars that we know.
Yes. 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 So one has to be careful with this low spin assumption is, I guess, the point. It's maybe if you just want to do a first guess, it's maybe not so bad, but you should be really careful because there are other systems that might not have low spin. And then your interpretation would be biased if you assume this.
So about this plot, if I'm reading it correctly, any measurement with any value within this range of 3 orders of magnitude more or less would be the real value.
Yes, it's consistent with the measurement to 90% confidence, let's say.
Is there an estimate of like how much is this band gonna shrink with future detectors?
Yeah, so usually you can kind of estimate how errors shrink as 1 over the signal to noise ratio. So if you have a 10 times better signal to noise ratio, very roughly you would get a 10 times better measurement. And yeah, in future detectors, we will have much larger signal to noise ratio. And this was also during the second science run observing run, so already in 2015. So even now detectors are already much better. So if it happens now, well, now the detectors are off, but at the end of March or April, then yes, we could have tighter constraints. Anything else about this? Because I think now we're out of time again. So maybe let me just say the next thing to look at would be, of course, the time-dependent perturbations relevant for the ring down, which would use a similar setup as here. So again, you have a decomposition into 2 sectors with different parities. You have these perturbation functions, but now you have to keep the full time dependence and then solve for the quasi-normal modes, which are modes with, well, maybe I even show the plot, which are modes, if you think of this kind of scattering problem of waves on a black hole, where you have only ingoing waves at the horizon and only outgoing waves at infinity. So no, you don't have any incident and transmitted waves. And those are the boundary conditions, and that make it into some sort of an eigenvalue problem where you only find solutions for certain frequencies, which are the quasi-normal mode frequencies.